All right, so let's start with the topic of gravitation. And what are the subtopics in gravitation? Entire thing is based on Newton's universal law of gravitation, which gives you gravitational force. So we'll go through some things related to force. Then there's a concept of gravitational field, gravitational potential energy, gravitational potential, orbital motion, planetary motion, satellite motion, and escape velocity. Kepler's law is part of orbital motion. So these are the various subtopics which we need to will go through one by one in case of gravitation. And you notice some of the things are very similar to what we have come across in case of electrostatics. So you should have, we have done it recently, so you should have some memory of the same. So let's look at that. Let's just start with it. So what is law? Law is very simple. I think most of you remember the formula. This is for, see, this law gives you gravitational force of attraction between two point masses or point-like masses. So these two are like point-like masses. And what is the direction? Also gives you direction. Direction is along the unit vector. Okay, and it forms an action-reaction pair. And this is a pretty simple thing. And we also understand if we have any spherically symmetrical mass, for any space outside, it behaves like a point mass placed at the center of the shell or the sphere. So these are things we know about forces. And what is gravitational field? Gravitational field is similar to electrostatics. In electrostatic, any point charge creates an electrostatic field at all points in the space. Similar way, any point mass also, it creates a gravitational field at all points in the space. So what is gravitational field? Is force per unit mass. So gravitational field at a point. So we can define gravitational field at all points. Only thing, the point itself should not contain a point mass. So gravitational field at a point not containing a point mass due to point mass or system of masses is equal to vector sum of force experienced by a unit mass placed at that point. So if I have some number of masses m1, m2, m3, what we'll do, how do we calculate field at a particular point? We'll calculate field at a particular point by placing a hypothetical unit mass, calculating force experienced by unit mass due to each of the mass which is part of the system present, and take the vector sum. Okay, and field due to point mass or also due to spherically symmetrical mass at a point outside is equal to Gm by R square. And negative is attractive force. And another important point we need to understand, if any particular point, if field is given, field is E, if we place a mass M at a point having field E, it will experience force M into E. So these are very basic points we need to understand. And then we come across, this is fine. And in case of Earth's gravitational field, on the surface, Gm by R square. So here we take mass of Earth and radius of Earth. Variation at a distance r from the center for any point outside, if r is greater than capital R, it becomes like a point mass. Field becomes Gm by R square, small r square. And at a, just to understand here, at a height r from the surface, if you have to calculate gravitational field at a height r from the surface of Earth, we have to first think of what is distance from the center of Earth. If height is r, the distance from center becomes 2r. If distance becomes 2r, it varies as one inverse square law. So if distance becomes twice as much, gravitational field become 1 by 2 square, it becomes G by 4. So at a distance of 10r from the center of Earth, it becomes 1 by 100 times, so on and so forth. For small height, so I can return, to calculate for a small height, I can write it as Gm divided by R can be written as R plus height into square. And if height is small, through approximation, we can also arrive at height h, gravitational field is equal to G1 minus 2h by R. Within Earth, it varies linearly. And so it varies linearly from center to max. So if on the surface of Earth, if gravitational field is G, at a distance of 3r by 4 from the center of Earth, it becomes 3g by 4. At a distance r by 2 from center of Earth, it becomes g by 2, and so on and so forth. At a distance d, it becomes g1 minus d by r. Very simple. If distance is d, r becomes equal to r minus d. Same formula. So it varies linearly. That's what it is. So outside it varies inverse square law. Inside it varies as decreases linearly. And there's effect of rotation. Effect of rotation I will take up in form of example. So we'll understand it also gets affected due to rotation of Earth. So what is the Earth? Yes, G is on the surface. As we move away from the surface, G decreases. It decreases 1 by r square. As we go nearer to the center, again G decreases linearly. For small displacement from the surface, these are the two approximations, and due to rotation. So that's all related to field and force. So let's look at some questions based on this. They are simple questions just to refresh your memory. Three uniform spheres, each having mass capital M, radius r, kept in a such a way that each touch other two. What is the magnitude of gravitational force on any sphere due to other two? So let's visualize what the question is, and it's a very simple question. These are three spheres, and see, we are looking at force on points which are outside the sphere. So all three cases, we can assume we can replace the sphere with a point mass placed at its center. So this also is M, this also is M, this also is M. And they will form an equilateral triangle of length 2r. Okay. Now, if I have to calculate force on any one of the sphere, this will experience force due to this sphere plus this sphere, and both forces are going to be attractive in nature. So if I mark the direction of force acting here, this force will be F, and magnitude of this F will be equal to G into M divided by 2r square. And due to this force also, force is F. And it is acting at an angle of 60 degree. The resultant force will be equal to root 3F. So resultant force, this multiplied by root 3, that's my resultant force. So these are very simple question, and all of you just refresh your memory and do that one. Let's look at this question here. A number of particles are there. They're all like point masses, or they're spherically symmetrical masses, and nothing is inside the spherical shape. So what is given here? Okay, all are separated, all distances are d by 2, and this, and okay, whatever distances are given here, and this distance is, okay. So these are all different masses placed here. What we need to calculate here, we need to calculate magnitude of net gravitational force on the central particle. So we need to find what is the net force on this mass here. And there are a number of them present here. So what we do here, we need to make use of symmetry here. What is symmetry here? If I take up, what is the advantage? Forces due to equal masses on either side at equal distance are equal and opposite. So what does it mean? If I take these two masses, if I take these three together, so these two masses 5m and 5m are on the opposite sides, equal distance along the same line. So this also will apply force of attraction. This also will apply force of attraction, and they are all collinear, it will cancel out. So I can cancel all such opposite forces which are on the same line on the opposite side of M. So similarly, if I draw this line, this 7m7 also gets cancelled. This 4m also forms a pair, gets cancelled. This 2m also will exert 0 force on M. So what is the net force? Force exerted on M is only due to this here. So that's taking advantage of symmetry, and we can easily find forces if any such question comes. Similar thing we do in case of electrostatics as well. Okay, now come to, this is also past means question. What is given here? The straight rod of length L extend from x is equal to A to x is equal to L plus A. Okay, and we need to find gravitational force this rod exerts on a point mass M at x is equal to 0. So let's see, this point is what is given here. This is x is equal to 0, and this is x is equal to A, and this end is x is equal to L plus A. Of course, length becomes L. And its mass per unit length also is changing. Mass per unit length of the rod is varying like this. We need to find force on this. So here we know gravitation law only due to point masses is a line mass. So first what we need to do, we need to break into a small random element. Let me take a random element here. This random element at a coordinate of x here. From here, let the distance be x. And length of the piece be equal to dx. That's what we have done so many times. I'm just doing it so just to refresh your memory. And let this mass be equal to dm. So this mass, now these two become like a point mass. I can use gravitation law here. Dm will be equal to lambda into dx, but lambda also is a function of x here. So we have to use lambda x here. lambda x is equal to a plus b square into dx. That becomes my dm, mass. So mass of this small random piece is this value here. So what is force of attraction? G into first mass into second mass divided by square of the distance. So this is the force which will act on M due to this mass here. Which direction of force will act? Force will act in this direction. And all are in the same line. All elementary pieces also will exert force in the same direction. Hence, though it is a vector quantity, I can simply integrate and find a resultant. What would be my limits here? If I substitute here, limits will be this is the closest piece, this is one end, this is the farthest piece. X is varying from a to L plus a. So limits of integration will be a from a to a plus L and gm, and we substitute this value. It's a simple integration, and we can find the force this rod will exert on point mass here. This is basic application of integration process. Right, so we'll stop here and we'll continue. So good afternoon, everyone. So we continue with gravitation, and we were calculating force and field. And let's look at this question. This is one of the very tricky and nice question which had come. And let's see. This question, okay. Let me tell the gist of the question. See, this is something what is given the question. There's Earth here, and say initially what is here? Initially this is sun here, and sun has certain mass. The distance is d. What this question says, difference in the force exerted in the nearest and the farthest point on the earth. So if we keep a point here, then this is something about, okay, let's see. What it says, if I keep a mass here, it will experience a different force due to sun. If I keep other mass at the other extreme of the earth, it will experience a different force. So because of sun, force experience, delta F represents difference in force. Delta F1 is difference in force due to sun. So initially we calculate delta F1 due to sun, and then we replace this mass with moon. In case of moon, this mass will change and distance will change. So this is what the question was, and then you have to find what is the delta F1 and delta F2. So what is delta F1? Delta F1 is difference in force experienced by unit mass at the nearest point and the farthest point. So this will be greater, this will be smaller. So how we go about solving this question? See here, so in case of this, so delta F will of course depend on M value. It will depend on D value. It will also depend on radius of Earth, because these distances are based on Earth radius. So let's take this case here. So what is F max here? Let's write this term. It is D and radius of Earth is R. So maximum force will be equal to G into mass of the sun, if we take sun first, and whatever mass we place on here, M mass here. And first one is D minus R square, and F minimum is this expression. So these are the two expressions we get here for particular value of M and D. Now, what is the difference? The question is about the difference. When we calculate difference here, F max minus F min, you can just simplify it. It come equal to GMM. We get 1 by D minus R whole square minus 1 by D plus R whole square. And when we simplify, and here all we need to do here, we need it based on the information given. Also, we can easily figure out R is much less than D. If you make this approximation, so whenever question is about ratio, I will only look at which quantities are varying. So which quantities are varying here? When the sun is replaced by moon here, this M varies and D varies. So I have calculated delta F in terms of capital M and dq. So difference in maximum minima is proportional to mass of this planet here and divided by dq. This is the distance. So when we have, this one is repeated for two cases. When we calculate delta F1 by delta F2 here, what is delta F1 here? Let's delta F1 be the difference of force exerted by the moon at the nearest and the farthest point. This is related to moon. So I'll write mass of the moon divided by distance from the moon q and divided by delta F2, which will become mass of the sun divided by distance of earth from the sun q. So this question is based on, see, in terms of concept, there's nothing new. It is same force between two particles here. But the way the question was given, and now we substitute the value. So what is the mass of the sun? What is the mass of the moon? What is the distance? And you can get an answer. So all of you just go through, see how do we and you how do you solve this one? Okay, this is a relatively simpler question from a sphere of mass m and radius r, and this kind of question we have done multiple times, and all of you should be able to solve. So I'll give a couple of minutes for all of you to solve. So a sphere of mass and radius r, a smaller sphere of radius r by 2 is cut out from here. Okay, and the part which is created a cavity here, this cavity is made in original sphere, and this cavity is kept here, and this is the false sphere again, and is placed at a distance of 3r from the center of the larger sphere. Okay, and what we need to do here, we need to calculate gravitational force between this sphere with the cavity and the other smaller sphere that gets formed. So all of you think, how would you calculate? So I'll give a couple of minutes, think of how do you solve this question per position. See, in this case also, what we do here, let me call, this is, okay. So the force experienced by this mass here, let me call B, is equal to force experienced by mass B due to full sphere minus the force experienced due to cavity. That's the force it will experience by principle of superposition. So first I will calculate force between full sphere and this mass m by 8. And since these two are not overlapping, I can replace this entire mass at its center and this entire mass at its center and the distance 3d. And then what we'll do, then I'll calculate force between this sphere and if the cavity was there, because between the cavity mass alone. But cavity mass will be, I will again, since the cavity mass also is spherically symmetric, I replace with equivalent mass at its center, this mass also center. So this distance will become equal to, this will become m by 8, and this is anyway m by 8, and the distance will be equal to 3r minus r by 2. I'll calculate this force. So what is the force on this? Force on this is due to full sphere minus force due to cavity sphere. I calculate two forces and take the difference of the two. That's the approach to solve here. Center mass is not necessary. Yes?
Sir, is like gravitational force, is it necessary that it always acts between the center of mass of two objects?
See, first of all, gravitation is not defined for any other shape. It is defined only for point mass. Then we say if mass is spherically symmetric, I can replace for any point outside. If I have to find a force between one spherical shell and a solid sphere, how would I find mass? Since it is spherically symmetric, for any point outside, I can replace with equal mass based at the center, and this can be derived. So that's what there's no concept of center mass which is coming in here. It is not force between center mass. So don't bring center mass whenever we talk about gravitational forces. Okay, it's only superposition. And for a smaller sphere, the force on the smaller sphere will be force due to the full sphere minus force due to cavity part. That's the principle of superposition. Mass of the removed part is m by 8. So full mass with this g into m by 8 and divided by 3r square. That's the force due to a full sphere was present. But now we are removed. So we are just calculating in fact the removed part. The removed part also is a sphere. That's why I can do it. Had it been something else, would we have taken center mass? No. Center mass is not between center mass. We cannot apply that concept here. Okay. So in cavity part also, if we calculate very easily, I think I have not written that part. Force due to cavity part also will be equal to g into m by 8 into m by 8. And what will be the distance in that case? Distance will be 3r minus r by 2. So then that will be the distance here, r by 2 whole square. And we take the difference between the two. So just to extend your logic, suppose if we have two cubes here. So I have a cube of mass m and side L, and there's another cube also, which is also mass m, and this also side L, identical cube, and distance between center is equal to L. Can we say the force between these two will be equal to g into m into by L square? No, it is not. Okay, so this extension, this is only a formula what we have, or law what we have is only in point-like masses, and we extend it for symmetrical masses, spherically symmetrical masses. Anything else we need to break it down and calculate. So we cannot extend even with this also, even simple case also. it's not easy to calculate what the force between two cubes will be. Okay, now moving on. So all derivations are dividing into small pieces and taking small elements. So this system consists of thin ring of is a thin ring of radius r. So there's a thin ring here. This radius in r given here, and there's a long uniform wire oriented along the axis of the ring with one of the end coinciding in the center of the ring. So this one mass here in blue color, and this other line mass which is going like this, starting in the center, reaching up to infinity. If mass of the ring is m, so this has a mass m, and mass of the wire, since it's an infinite wire, we cannot give total mass here. It is lambda per unit length. What is the force of interaction between ring and the wire? Okay, so that's what we need to calculate. See, again here, can I use direct formula? No. So way to calculate this be, see, first one way, if some of you may recall, if I take a small element here on the y, so I have taken a small element here, and we can take this at a distance of whatever, I think I have taken r or whatever, at a distance x from here, and length of the element is dx. So when we calculate force on this small element due to small circular element, I have to divide the circular into very small pieces and calculate force. Or otherwise, what we can do, we can calculate. So each part if I take, but because of symmetry, you have done something in case of electrostatics also. If I take a small element here, and if I take a diametrically opposite element here, what will happen? The forces will be equal and they'll be like this. The perpendicular component cancels out, radial component only adds. So if we do for all elements only, a radial component will keep adding. And conceptually what I can do here, and we can derive that part, which I have done in case of electrostatics. But in terms of understanding formula, if entire mass of the ring, if I place at one point, so entire ring I have placed at one point. So this also magnitude of force will remain same. And if I take the radial component, that's the resultant force. So if I place entire mass m here, and this is dm here, if I have to calculate field at this point, let me calculate field at this point. How would I calculate field? If distance is x and this is r, field at that point would have been g into m divided by square of the distance. The square of the distance is r plus x, r square plus x square. But this field will be in this direction. We need only the radial component. So if this angle is theta, I need to multiply into cos theta. That's the formula. I'm just telling how the formula is derived. This is what we have done in case of electrostatics. So field becomes gm divided by, and cos theta is how much? Cos theta is x divided by this. So this becomes my formula of field. This is my formula of field. So let's apply this case here. And this case also, we have not used any center mass concept, nothing. We have just taken two basically point-like masses. So force on a random element, if I calculate field, force on the random element is field at x into mass of the small element. Mass of the small element will be lambda into dx. I need to know the formula of field at a distance x. If we don't know also, this is how we can arrive it. Once I have the field, rest becomes very simple. X equal to gmx, r square plus x square raised to power 3 by 2. And even if you don't remember, this is how we can calculate. Place entire mass at one point and calculate the magnitude of field. Take the axial component, that's equal to my field here. And then we have to integrate. So if I write this term here and add that lambda dx and integrate from where to where, from 0 to infinity, you will get your answer. So this also, all of you must try and solve that one and see you get your answer. Integration is fairly simple one. There's x term, so we simply make simple substitution. R square plus x square equal to t, you get your answer. So Jaideep, have you understood?
Yes, sir.
What are the key point to understand here?
Either we can derive the whole formula, or we just remember.
No, other thing what I'm saying here, see, many times we think in case of gravitation also understood cube also, we cannot take the force between two cubical masses to be equivalent to point mass space at the center of the cube. We can do only at the center of a spherically symmetrical mass, not otherwise, and that also can be derived. Okay.
Yes, I understood.
So don't take center of mass kind of stuff. And whenever take gravitation, it is not between force between center of masses. That's the point we need to keep in mind. So let's another case. What is gravitational force in case of spherical shell? Between a, sorry, actually say hemispherical shell. This is how the figure is done. Shape is spherical. So this is of mass m and radius r. Sorry, yeah, there's a spherical shell of mass m of radius r and a hemispherical shell of mass m and radius capital R. What is the force between them? That's what we need to calculate. Okay. So in this case also, again, whenever spherical symmetric is there, since this mass is spherically symmetrical, for purpose of calculation of force on any particle which is outside or for calculation of field, I can assume this entire mass to be placed at its center. So if I have to calculate field due to this mass, I can calculate any point on the surface of a hemispherical shell. The magnitude of field will be equal to Gm by capital R square. That's the magnitude of field. Okay, and which direction the field will act? The field will always be directed towards the center of a smaller sphere. So every particle on the outer spherical shell will experience a radially inward force. Okay, so and that's how the force is. But we need to calculate the resultant. We have done something similar in case of electrostatics, and this is something we do in case of fluids also. So it will experience a pressure kind of force. Force per unit area everywhere on the sphere will be constant, which you can call as pressure. The force or radially inward pressure will be equal to mass per unit area into field. That's the pressure it will experience. Sigma is mass per unit area and E is the field at all points on the hemispherical shell. So do we know the value of E? E value is Gm by R square. And what is sigma here? Sigma also. And so if once we have pressure value, what is the resultant of pressure in the vertical direction? Of course, resultant will be in the vertical direction. Resultant force will be equal to pressure into projection of the area. Projection of this hemispherical shell will be a circle of radius r. So resultant force will be pressure into pi r square. That's the force. Rest of it, I think you can easily write here. What is the force equal to? So I written mass per unit area. Total mass is m, and it is a hemispherical shell. So 2 pi r square, and field is equal to Gm by r square, and projection of area is pi square. Thus, the force of interaction between this, either it is solid sphere or spherical shell. Both cases answer is same. So this is what. Next one is something like this. Gravitational force. I am just doing something which are a little different from the rest. Gravitational force between spherical shell of mass m and radius r. And sorry, I think this is something I have questioned earlier. Okay. I think I questioned. Let's look at this. Ignore that part. This is a fake question here. You have a circular ring of radius r. This has a mass m, and there's a sphere of this has mass m. This also has a sphere, also has mass m. Its radius is r by 4. It is kept on the axis of a circular ring at a distance of root 3r, r being the radius. Now, what is the force between ring and a sphere here? So whenever force is experienced by a spherical object due to masses which are situated outside, for purpose of calculation of force on a spherical object also, I can replace with this a point mass. So this, if when I'm calculating force on this sphere due to circular ring, I can replace this sphere with a point mass m placed at its center. So if I have to calculate force, now it becomes very simple. Force explain this mass m due to the ring will be equal to m into field due to the ring. And we have already done what is the field at a distance x due to the ring, field due to x due to the ring. Again, I'll write this one, g into m, x is the distance, divided by r square plus x square raised to power 3 by 2. And then in this case, r square plus x square is easy. X is equal to root 3r, capital R square, r here, and we can calculate field here, and we will multiply this field by mass here to calculate, find out the force. I'm not spending more time because I'm just giving the hint. We are not solving question in the class. This is what all of you need to solve on your own, and it should get your answer. Bhagishri, is this understood?
Yes, sir.
Okay, so I think this is something I've copied. Okay. There's another question here. So this is two equal masses, each of mass m, are hanging from a balance whose scale paths differ in vertical height by h. What is the difference in weight in terms of density of Earth? So what does this question mean? So first of all, basically what it says, if I measure weight near the surface of the Earth, I'll find some weight. If I go to another point, which is at a height h from the surface of Earth, I'll find a different weight. And what is the difference in weight? That's what this question is. And give the answer in terms of density of Earth and radius. So this question, though wordings look a little odd, but the solution is extremely simple. It's based on the two things here. It is based on as the distance from the center of Earth changes, gravitational field will change, hence the weight also will change. And what is weight? Weight at a point is equal to m times gravitational field at that point. And what is gravitational field at a distance r? It is gm by r square. So it is based on these two concepts here. And since the height is small here, difference in weight will be equal to m into g at a distance r and minus g at a distance r plus h. Those are the height differences. Essentially what I have taken, first point I have taken on the surface of Earth. This is taken at a height of r plus h. Sorry, at a height of h here. So do we know the value of g and do we know the value of r plus h? We know the value and we can substitute and easily you can get your answer. Okay. So for this, but this is since h is small, the difference in g, so we know what is g at a height h, we can easily get an answer. So the difference of these two will come equal to 2h by g into 2h by r. So difference in weight is this. Okay, this is a little different question and let's try and understand here. Find the difference between center of gravity and center of mass of two particles attached to the ends of a light rod equal to length of equal to radius of Earth. So there's a light rod here. It is equal to radius of Earth. This is radius of Earth. This is mass Earth. So if I have one mass here, another mass here, there are two terms, and many times we take two terms as identical, and these two terms are not identical. What are two terms here? Center of mass. We know what is the center of mass here. If you have to find the center of mass, we find the r value, position vector of center of mass, two-part system, m1 r1 plus m2 r2 divided by m1 plus m2. So this is fairly simple. We know this is position of center of mass. But if I have to calculate what is the position of center of gravity, in that case it is equal to m1 g1 r1 plus m2. So we replace mass by gravitational force on the mass. And if these g values are equal, let me write that expression. And this is about m1 g1 plus m2 g2. So what has happened here, in place of mass has been replaced by its weight. And if masses, all the masses are placed in a space where g is same, g1 will equal to g2 and all g terms cancel out. So position of center of gravity and position of center mass coincide. But if masses are placed in a space where g value is not uniform, these two are not the same. So this question is only to make that point clear to everyone. How do we calculate? So first of all, I hope this definition or understanding of center mass and center of gravity. Center of gravity, this is mass alone, and this is gravitational force acting on the mass. Then we divide by the sum of these two. Let's do and calculate in this case here. Okay, so the one mass is here, another mass is here. So let me calculate, this, if I take r vector like this, and calculating with reference to point O here, what is the position of center mass here? Center of gravity, this is center of gravity, m1 g1, and this is the formula here. It coincides with center mass if gravity is uniform. In this case, g value here and g value here are not the same. That's why the two will not coincide. So center mass is very easy to calculate here. M into r divided by multiply m into 0 divided by 2m. So center mass will come at the midpoint, which is r by 2. Center mass doesn't get affected by what is the gravitational field. Now let's calculate what is this term will be. Center of gravity. So if I call this mass as first mass and this mass the second mass, here the value of g is 0. That's what you should understand. If I call G1 is equal to 0 and G2 is equal to G on the surface of Earth. So if I write center of gravity, I write mg for this term mg into r, and this one will be m into 0 into r. This term becomes 0. And when we divide also, what is the term we divide with? M1 G1 plus M2 G2. So one of the term M1 G1 is equal to 0. So divided also mg. Center of gravity is equal to r. Because this will not experience any force, and so it remains r. So distance between center mass and center of gravity becomes r by 2. So this is something, just pay attention. So whenever question comes on center of gravity, see in any other form, if two different values of g's are given, you should be able to find what the center of gravity is. Okay. This also is another question which had come in the past in mains, and a really tricky question. Okay. So there's a planet. The radius of the planet is 1/10 of the radius of Earth. So if I call r being the radius of Earth, so I have drawn a figure of the planet. Its radius r is equal to r by 10. Let's do that. And it has same mass density as Earth. So entire planet has uniform density, same as Earth. So scientists dig a well of depth r by 5. So for whatever radius this planet had, we have dug a well of depth r by 5 here. And a long wire of same length. What is the red color? Red color is a wire. It is extending from surface of the planet to the bottom of the well of same length and linear mass density. It has a wire. Its mass per unit length also given 10 to the power minus 3 kg per meter is suspended here. Now, if the wire is not touching anywhere, so it is not in contact, only thing you are just holding the wire at the top. Then the force applied at the top of a wire by a person holding it in place. So this wire also, whole wire would have fallen into the well unless you hold it. So question is, what is the force somebody need to apply on the wire to hold it? That's what we need to calculate. The radius of Earth is taken as 6 into 10 to the power 6, and acceleration due to gravity on the surface is 10. So that's what the question is. So there are multiple things in the question which we have to understand. See, if the density is rho here, as long as the density remains constant, we understand the GR is proportional to R here. For this planet also, since the density remains same, radius is 1/10. On the surface, gravitational acceleration will be equal to G on the Earth's surface divided by 10. That's the first thing you need to understand here. This is nothing but is equivalent to from Earth, solid Earth, a core, a central part of Earth of radius r by 10 has been cut and removed. So what would have been G there? That would have been GE by 10. So thus, so gravitational field on the surface of this planet is equal to G by 10 is equal to 1 meter per second square. And from here also, it will vary linearly. If I look at G value, how it vary on the surface, it is 1, and thereafter it will vary in the linear function, similar what we have seen earlier also. It varies like this. So force experienced by different parts of the wire will depend on value of G at that height. So force on different pieces of wire will vary. So gravity is exerting force on different pieces, and we add up all the forces exerted by gravity, either through integration by summation. To hold this wire in place, we have to apply equal and opposite force. So this force is equal to gravitational force on the wire. Force what we need to apply is equal to gravitational force on the wire. And since it is varying, we need to do in terms of a variable. So again, what we'll do here, since G is varying, I'll take a random piece. Every time what we do, we take a random piece, and we can call it either X or R. So let me take random piece. And since it is radial distance involved, at a distance R from the center, and length of the piece is dr. So, and the first thing you should understand here, how would G vary here? G will vary as 10 by R into small r. Same as Earth variation, because since rho is same. Then we do the force on a small element between R and R plus delta R will be mass into gravitational field at a distance R. The mass will be equal to mass delta mass is delta R, lambda into dr. Lambda into dr, and what will be G at a distance R? 10 by R into small r. Yes, Vignesh, what is the doubt you have?
Sir, we're supposed to take it as 1 by R into R or 10 by R into R? Like, because the G value is different, right, sir?
No, basically, I'm Okay, see, if in case of Earth, what we write G at a distance R. Okay, in
Yes,
this
sir.
case, also the density is same at a distance R from the center. Would the G be same as Earth or different?
Yes, it will be same.
It will be same. That's why I was just giving an example. So that's why I've written exactly the same. So as density is same, GR is same as what it would be for Earth. Capital R is the radius of Earth. Is this clear to everyone? Since density is same, and we can build a result. And actually, we could have written also, if density is rho, what is the gravitational field at a distance R? How do we calculate gravitational field at a distance R? It will be G into mr by r square. That's how we calculate gravitational field. Gravitational field will be only due to the mass enclosed within the radius r, and that becomes equal to G into mass within enclosed within radius r is density into volume divided by r square. And then we find this is proportional to r. Okay, and this, since the density is same formula is applicable. What is varied in case of Earth's gravitational field? And this expression, force on a small element, only thing I will now type dr term. So lambda dm, lambda into dr into gravitational field at distance r from the center. And force on the entire length, r is varying from here when we take the entire length. So r is varying from where to where? From this point to this point. What is this lower point? What is the distance? 4r by 5 to r by 5. So it is varying. The limit will be equal to 4r by 5 to 4r by 5 to r. Only thing what we'll do, final substitution, we'll put r is nothing but r by 10. So either I can substitute this capital R is equal to 10 small r, or this small r into capital R by 10, and we can find that answer. Okay, I'll stop here. And I hope until now all of you have understood and followed.